Hi everyone, good morning, welcome back to Pine Hollow Auto Diagnostics. Today we have an out-of-state 2015 Jeep Compass, 75,000 miles. Customer drove it here 3.5 hours away because its check engine light's on, it can't pass the emissions inspection, and he doesn't trust the local shops around. They already gave him their recommendation and he just thinks that it's not accurate. Let's see what the customer wrote, scan it for codes, see what's going on. Alright, here we go. Yep, 75,000 miles. Let's read the little note. 2015 Jeep Compass. Greetings, Ivan. This 2015 Jeep Compass has the money light on for a code P0038. Won't pass inspection. Headed to another shop and was told it needed a TIPM. I was not confident in that diagnosis, so wanted a second opinion. The rear O2 sensor was replaced with NTK from Advanced Auto on March 31st. Hope it's an easy fix. Place your bets now. Alright. Obviously, we'll start with a full code scan. So I got this saved in the PCM. There it is, P0038, O2 sensor, Mink 1 sensor 2, heater, circuit, high. Okay. We'll come in here. And let's just take a brief look at the live data at the oxygen sensors and the heater element. So we have sensor 1.1, that's the upstream, and sensor 1.2 is the downstream. So we're interested in sensor 1.2 volts, and 0 to 1 is the familiar OBD2 translation. We also want to see the heater pulse width. Apparently it's a pulse width controlled heating circuit, and it can also measure the heater temp on each sensor. We don't know how the circuit works yet. We'll do our research very soon. Let's compare it to the upstream sensor. Sensor volts, heater, heater temp. I don't know what sensor level is. Well, let's just look at these. Graph these. So car's off. Look at that. Sensor 1 volts 3.6, and it's cooling off, and we're coming back up to 5 volts. So on Chrysler's, on the signal, it's a 5 volt bias, and then it gets pulled down as the sensor heats up. Look at the downstream. 5 volts. Heater temp is minus 83 degrees Fahrenheit. Upstream is plus 960. So already this doesn't make sense. 2.47, that doesn't make sense. And the heater is 0%. Okay, so let's fire it up. Look at that. The upstream turns on. It instantly starts oscillating. So these are the real volts, and these are the translated volts, 0 to 1. So you can see it's 2.5 volt difference there. This is a nice screen capture. There's definitely something wrong with the downstream sensor. And look, the heater is now at 50% duty cycle since the sensor heated up. You can measure the sensor temperature, it looks like. Downstream's dead in the water. Okay, great. So take a picture of that. Now, let's go in all data, look up this code, see what the code setting criteria is, see what the circuit layout is, and do some basic checks to pinpoint this issue. So without doing your research, doing a diagnosis like this is, you won't have much success. Let's read up on this P0038. So, there's our PCM. These are the two oxygen sensors. We're worried about the downstream oxygen sensor 1/2. So, on the picture, this is our signal circuit. So, the return, and then there's the oxygen sensor, and it varies the signal right here. Then we have the heater circuit. So, directly power side fed by the PCM, heater control, and then it's just tied to ground. Okay? Now let's read theory of operation. This is very important. We want to know how the PCM knows these parameters and how it's controlling this heater. So the primary objective of the heater control is to attain the fastest possible temperature rise. This allows the system to enter closed loop quickly and meet the OBD2 requirements for continuous monitoring, deliver accurate readings. Yes. So it's a pulse width modulated current to the O2 sensor's heater element. The PWM duty cycle is calculated in response to the temperature measurements. PCM uses the collect information to continually adjust the PWM to achieve a desired steady state temperature target. Interesting. So it's a smart heater circuit. Heater temperature is obtained by measuring the heater resistance and calculating the heater temperature. Using the resistance versus temperature characteristic in order to measure the heater temperature, transistor that controls the heater is momentarily disabled and current is passed through a precision sense resistor connected in series with the heater element. The voltage drop across the sense resistor provides a relationship to current which equates to a temperature value. Okay, very neat. Once the temperature is acquired, the sense current is turned off and normal operation is restored. The actual heater temperature is monitored continuously and the heating rate is adjusted to prevent damaging the heating element. So this switch between putting out current to heat the sensor and turning it off and then measuring the resistance, I think happens very quickly. It's on, off, measure the resistance, turn the heater on, measure the resistance, the continuous closed loop feedback system on the same control wire. Very neat. And what we saw in scan data, the pulse width modulated signal is just 0% and the temperature doesn't make any sense. It's like minus 80 degrees. So, what are the variables here? Bad engine computer, broken wire, on the heating, the command wire, or a bad sensor ground. So the whole circuit needs to be continuous, as we see right here. So from the computer to the sensor through the heater and then to this ground point. Let's read when it's monitored. Okay. PCM detects the O2 sensor heater element input is above the maximum acceptable voltage. Okay, that's an interesting set condition. And it says possible causes O2 sensor heater control circuit shorted to voltage. Interesting. Or the oxygen sensor itself is bad, or the PCM is bad. So 3 choices there. Roll the dice, and this one's already replaced. So what's next? The PCM, or there might be a wiring problem, right? Let's take a quick look through the flow chart, see what they recommend that we check. Check the heater control circuit for short to voltage. Okay. Is any voltage present? Then it says check the O2 heater control circuit for an open or high resistance. Okay, so if it's a broken wire, would it set this code? Not according to this. Doesn't say broken wire, but yet we're checking for an open wire or high resistance. And then the last check the O2 sensor ground circuit for an open. Okay, so they are checking for an open circuit. Interesting. And they are using test lights, which is great. I love it. And then finally the oxygen sensor. They want you to substitute a test light for the sensor. Again, that's a great check. And we'll do that if we need to. And then check PCM, blah, 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 blah. This is replace PCM. Okay, so that's our whole flow chart. What's the next easiest, most informative check we can do? I'm thinking, we'll find this pin at the PCM and we'll put a piercing probe on that wire. So all the circuit's intact, we just want to probe into that circuit. Then, with the vehicle off, we can just do a simple resistance measurement from that wire to ground to see if the path through the sensor is continuous. I expect a resistance of 10 ohms or less. That's a typical oxygen sensor heater resistance. If that checks out, then this is a pulse width modulated circuit, so I want to put a scope on there and measure the voltage. You can use a regular meter, but let's say you get 6 volts, then is that voltage just stuck at 6, or is maybe there's a 50% pulse width modulated signal on there? You won't know with a regular meter. So for any varying voltage signal, my rule of thumb is just use the scope. You'll get more accurate information right off the bat without guessing. And that's the name of the game. No guesswork. We want guaranteed diagnosis as quickly as possible. Okay, so O2 heater control, we're looking for pin 48 on connector C2 at the PCM. So location, powertrain control module C2, it's right on top of, looks like top of the airbox, the connector that's closer to the front of the car. There's 2 connectors. And then here's the pinouts, pins 1 through 24, 25 through 48. That's the one we want, is pin 48, so it's going to be right on the side of the connector that doesn't have the wires on it. And it's going to be the second pin. And just double check, 48, there it is, O2 1-2 heater control supply, brown and red wire, so that should match up. And it should be right next to pin 24, and 24 is O2 1-1 heater control wire, brown and orange. So brown and red and brown and orange. There it is, brown and orange, brown and red. Let's go find that wire and put a probe on it. Alright, this is beautiful. PCM is right up here, easy access. So what I want to do first is just pop off this plastic cover from the top. Awesome. And now we're looking for brown and red and brown and orange wire. So that's brown and orange. That's brown and blue and tan. So right off the bat, that does not make sense. Our wiring colors are not consistent. So it's a blue and orange. That's a blue and tan. Let's do a little more research, make sure we have the right wires. Alright, that was my fault there. So pin 1 is here, 24 is here, so 48, there's our brown and red wire right next to the brown and orange. So those are the heater control wires. So we're just going to install a piercing probe right here. And some people might say, oh, why don't you just back probe the PCM connector? A few reasons. Chrysler actually does not recommend back probing because when the pin goes through, A, it disturbs the weather pack, B, it can actually spread the terminal there, so you'll have poor pin fitment issue if you back probe. 3, you might back probe, and if you're not perfectly straight, you might cross to another pin and short something out or get a wrong reading. Too many variables. So a nice small tiny little hole right here is not going to harm anyone. If you really feel the need to, you can seal it up. This is a nice dry environment, not a constant battery power wire that's going to grow green crusties. So not worried about that at all. This is the most accurate way to do this measurement. So let's hook up just an ohm meter right now, measure the resistance from here to battery ground. Okay, so we're measuring resistance from this wire through the sensor back to battery ground. And what do we have? 4 mega ohms. So we confirmed just with this one measurement that we have an open circuit somewhere between the PCM, the sensor, through the sensor, and then back to the sensor ground. So this is not going to be a computer problem. At least it doesn't look like it. So now the next step is to go to the sensor and check for continuity from here to the heater pin and also the heater ground. Let's jack up the car and get to the sensor connector. By the way, since we're here, turn the meter 1 notch to volts. See, the voltage is floating. That's a red flag for an open wire. We want to make sure that this is not shorted to like a battery, constant battery power or something like that, because that was one of the code setting criteria. But the code setting criteria never said open wire could cause this problem, even though in the flow chart they checked for an open wire. That's interesting. Alright, let's get under the Jeep. It's safely jacked up on jack stands. And here's our downstream sensor, brand new. The wires go over the drive shaft to this connector. Beautiful. So, 4 wires. Let's see on the wiring diagram which ones we're after. It's going to be the brown and red is the feed, and the black and light blue on pin 1 is the ground return for the heater circuit. So let's identify the wires. There's a brown and red, there's a black and light blue. So let's unplug this thing. Oh, it's already unplugged, I guess. And use a test light to first verify the ground pin. Now for this test you're going to need a known good power and ground, and test light 300 milliamps is fine. So if we find a ground, test light from battery positive, if it finds a ground, it's going to light up my test light. So let's touch it to the black and light blue pin and see if the test light actually lights up. Look at that, it's not lighting up. Perfect. Let's verify wiring integrity on the brown and red. I'm sure that's fine. You know, what are the chances that there's 2 problems? And then we'll chase this poor ground. We could do a bypass test by providing this a ground and seeing what the resistance is with everything plugged in. That's probably not a bad idea. We could just back probe this with a test light to ground and measure the resistance of the circuit up top. And if everything's continuous, we're just going after this bad ground. Okay, sensor's plugged back in. I got my needle probe stuffed in the black and light blue wire through a test light to battery ground. Let's see what our ohm meter reads up top. On the resistance setting. Okay, 82 ohms, that's with the light bulb in place. That's fine. Let's see where the ground lives with the ground distribution, you know, where this ground terminates. So what we just determined is there's no continuity to ground from pin 1, so there's either a broken wire or it's bad at this terminator, you know, at this end, but there's no label here. So we have to go to Catalyst Monitoring System diagram, and here we have G906A. So let's look up G906A. So in the ground distribution for G906A, we have lamp assembly left front. Now everything else works on the car. Left fog lamp, wiper motor, TIPM, and this oxygen sensor. It goes straight through to G906A. Where does that live? Over here by the left headlamp. Let's zoom in. There's a strut tower, looks like right here. So let's go inspect this and see if we find any green cresties. Now this is a clean Southern vehicle. You saw underneath, not a speck of rust, so if we find green cresties, I'll be really surprised. Well, the diagram is a little confusing. It's not near the strut tower, it's actually right here. And this is our black and light blue wire, looks like. Let's just give it a little tug. Now what we can do is back probe it right here and provide a ground and see if the ground is restored at the sensor before tearing this whole thing apart. There's just a little bit of corrosion on here, but that doesn't really mean much. Okay, there are actually 2 black and light blue wires here, and I can see they're crimped right to this eyelet, and they're not actually looking too hot at all. Oh, there it is. There's a bad ground. I'm sure the second one is not much better. So yeah, that's it. That's going to be our problem with this oxygen sensor. Now I have the test light from battery positive to this black and light blue wire, and it is dim. See, that's nice and bright. This is dim, and I'm sure if we back probe the second black and light blue wire, it's going to show open circuit. That's probably the one I just disconnected there. Oh no, that one's actually nice and bright. So it might be backfeeding through other circuits. See, there's a black and light blue wire. So this whole thing's a mess. We already have one wire disconnected. Let me find out exactly which wire it is, restore the ground to the sensor, and we'll fix this and should be good to go. Oh well, obviously the test light was dim because it's passing current through the little test light. So that is our problem confirmed. There it is, nice and dim. If we unplug this, the top test light will go out. There it is, confirmed. Tell the customer and quote them repair of this ground. It all looks nasty. I'm sure we're gonna have to strip back all these wires. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 wires here in this bundle. So we'll figure out how to make that work. So these grounds are a complete disaster, both of them. I'm just taking wires one at a time and just do a slight little tug, and they just snap right out of the ground. I mean, look at this. Chrysler should be ashamed of this poor quality. I mean, I have cars that are 20, 30 years old, never had a problem like this. And they live in the Salt Belt. This is a southern car, so this is completely unacceptable. We're gonna fix all this up. How do you prevent this? And what causes this? I really don't know. Poor quality something. Just ridiculous. I mean, so far it's just a check engine light, but soon you'll have lighting problems and fuse box problems. They'll probably replace the TIPM for no reason. Look at that, it's just a brown pus sack of corrosion. Alright, so here's my strategy with dealing with this mess. I'm taking bundles of 4 or 5 small wires, putting a big piece of shrink wrap on them, and then twisting the shiny, clean ends together, and putting on an appropriate eyelet, like so. We'll just crimp it down so it doesn't fly away. Make sure all the wires are snugly in there. You can see the exposed part is long enough to go all the way through. And then we're going to get a hot soldering iron. I might even use the benchtop HAKKO. Melt solder all the way through. Make sure the wires are completely covered so the corrosion can't get in like they did on the factory crimps. So people are like, oh, they only use crimps from the factory. Well, yeah, that leaves these exposed strands, and that's what corrodes. If you let the solder wick all the way up the strands to the insulation, and then reinforce that with some high quality marine shrink wrap, this will be all watertight and structurally sound. That's going to be better than factory. Okay, so this garbage. So we're going to have 1, 2, 3 new eyelets, and this one is still pretty decent. I'll just spray that with deoxit. We might put we'll just basically seal this up with some dielectric grease and tape and leave this eyelet alone. So let's do that. Okay, so this is the HAKKO FX888D, and I always have it set to 600 degrees. So this gets nice and hot, and we won't have to kill the battery on our little TS100. The TS100 would do the job, but you know, we have this right here. It's nice and convenient. We want to do a quality job. So let me do these two, and then we'll do the third eyelet. Okay, so that's at 600. So keep the soldering iron right on the eyelet. We want maximum heat transfer, and then start melting the solder in, and you should see it start wicking into the wire strands. So it takes quite a bit of heat to heat up all the metal of the connector and the wires, and just melt it all until you can't see any more copper. That's a high quality solder joint. Let's do the same thing with this one. And you see it gets so hot you can melt solder on this side of the wires and the connector. That's it. I'm happy with that. We'll let those cool down. Check the back side. If you see any exposed copper, just melt a little more on there. The heat shrink will cover everything, but we want to be 110% good. Okay, that's good. Excellent. We could even spray this with deoxit and flow some solder over all these wires to kind of reinforce that. Alright, let's toast on the shrink wrap. Very nice. We just have to bolt this on. We can put a little dielectric grease or silicone paste on this third eyelet. Try to seal it up from corrosion here. And then also on the stud. Just bolt it right up. So make sure the eyelets are nice and spaced out. Just make a nice tight sandwich out of all these. Super solid. Better than factory, or at least a bit better than the Chrysler factory. So I had the battery disconnected, by the way. Let's hook that up and make sure this thing is happy. Right before we start the Jeep, verification of repair. Again, we're measuring the resistance through the sensor on the heater circuit all the way to ground. 4.5 ohms. Amazing. So I feel good about that repair. Let's start it up and make sure no code set. Look at the live data. Okay, so scan the whole vehicle for codes. PCM codes are erased. The battery is disconnected. Let's see what the BCM says. Stored codes. Let's just erase these. Okay. No codes. Good. Let's go right into PCM. Look at that live data. And then the sensor 1. Okay. So they're both starting at 5 volts. We can see the temp is now realistic. Well, I guess that's as low as it can show. But let's fire it up. Look at that. Heaters are on. Temperatures are rising. It's a beautiful thing. Both operational within 15 seconds of startup. The cat will warm up eventually, but that's verification of repair. Love it. So that's it. Pretty straightforward diagnosis. Need a wiring diagram, test light, meter, no scopes required. But why would you recommend a TIPM for this problem? This circuit wasn't even on the TIPM, so I don't know where that shop was coming from. But fixed, no parts required. A couple eyelets, some solder. Okay, it did take a little while to make that right. So hour of diag, maybe an hour, hour and a half of repair. Customer is going to be so thrilled. Jeep's going to pass inspection, but keep in mind, it'll have to go through all the drive cycles again. With the oxygen sensor code, they may not have completed, you know, all the readiness monitors. So if that's the only code, then we're good to go, smooth sailing. If not, I'll ask them, you know, send me whatever other codes come up. Might have an evap leak, whatever. But that's it. So thanks a lot for watching. We'll see you next one. Bye-bye.